I'm Kumar. Welcome to my series on Newton's method, which is also called Newton-Raphson's method. Now, this method is an iterative process to get the approximate solution of equations. We'll begin with the basic concept. Let me sketch the graph of a function, and then we'll discuss the concept of finding solution using Newton's method. Let us say we have a cubic function. So let me sketch a graph of a cubic function here. We'll make a very simple one with one real root shown here. So that's the cubic function. We are sure that a cubic function will definitely have a solution, and this solution is called the root. So that is the root of the function, right? So let's say the function is a cubic function and we have a root here. So let me call this as r. So root. So root is the solution. I should say is the real value, which is the solution, and this normally is, rather always, is the x-intercept of f of x. Correct. So that is what we are interested in finding. Now let us say we found that this root is between two values. Let us say this is between two values. And how do we figure this out? At a value a, for example, we discovered that the value of the function at a is less than 0. The value of the function at b is greater than 0. So this implies that solution exists between a and b, right? So it exists between a and b. Open interval, since we know a and b both are not giving us zeros, right? So they are giving some values which are positive or negative. Now once we identify two values of x for our function where the graph crosses the x-axis, right? So wherever the graph crosses the x-axis, we have a root. Now how do we figure out this value? So what we do here is that we begin with one of these values, right? So we call that as our initial value. So in the iterative process, the idea is to start with some value. So in this case, let's start with x equals to b, this value, b. Now since we are just beginning with this, we'll call this as our first value of trial. So at this x value, on the function, we get a point, and this value on the function will be f of b, right? In our case, b is x1. So from x1, what we get is a point on the graph. So this point is x1, f of x1, right? So let's call this point as A, capital A. Now, at point A, if I draw a tangent, then what happens? See, if I draw a tangent at point A, let's say this is the tangent line at A. This tangent at A crosses the x-axis at a point which is very close to R, right? So what we do here is then we draw a tangent at this given point, which is x1, f of x1, correct? So this tangent, let's call this as line 1, right? We are calling this as line 1. Now this tangent will have another x-intercept, as you can see here, and we'll take this as our second point. So the first point we took was at B. The second we took as the intersection of the tangent with the x-axis. So that x-intercept, x2, becomes our second point, right? So x2 is basically a point which is closer to the real solution, right? Now, again, if we find the value of the function at this point, let's say we get a point B, in that case, if I draw a tangent at B, we approach a point very, very close to R, which let's call as x3, right? So at x2, we find the value, draw a tangent. At f of x2, right? Then again find the x-intercept and repeat this process, right? So basically the idea here is start at a particular point and we figure out this point is where, very close to where the graph crosses the x-axis, right? So the value of the function changes from negative to positive. Now once you select a point, then find the value of the function at that point, draw a tangent, find the x-intercept, again find the value of the function, draw a tangent, and repeat this process. Now once you repeat this process, you will approach the root, right? So you will approach the root. Now since this process is repeated, it is called an iterative process, correct? Now there is a formula which helps us to figure out all these values. So the general formula is that xn plus 1 is equal to xn minus value of the function at the nth point divided by the derivative at this particular point. So that formula is called the Newton's formula to find iteratively points which are closer and closer to the root of the function. Is that clear to you? Now, we'll do the derivation of this in the following part of the video. However, there is something very important to understand, and that brings us to the limitations or the restrictions, right? So let's also look into the restrictions. This method works beautifully with B as our starting point. Now, what will happen if we select A as our point? What happens when the first value is A? Now let's look at that part. Now if I choose A as my first value, then on the graph I have a horizontal tangent. Do you see that part? So the horizontal tangent will not have x-intercept, correct? And so the method fails. Do you see that? So if you select A in this particular example, you might land up in a situation where you do not have the correct result. You get the idea, right? Perfect. Now, there are situations when you can select a wrong point. For example, if I choose a point which is, let's say here, point C. Now in this case, for point C, the tangent is on this side, correct? So you get that as your second point, and that gives you a point which is farther away, correct? So in that case, what happens? Well, in this case also, you may get a solution after many trials, right? So So what you see here is that the process is very important. A important part of this process is your selection of the initial point, right? So that is kind of important to understand. So what we put a note here, and that is selection of initial point is very important. Sometimes you may not get a solution, sometimes you may get a solution, but after many trials, you understand. So we need to take a point where the values are converging to the root. Is that clear? Right. So that's kind of key to understand. So I hope that concept is clear. Now with this concept, let's move on and find the derivation of this particular formula. Okay. Now we'll again recall what we just did. Right. So let me make a small sketch here for part of the diagram. Let's say our diagram was kind of like this, right? So, and what we did was that we selected a point x1 somewhere on the right side of our roots, right? So we want to find this particular root as our solution. We selected a point x1 here. Okay, that's what we did. And then we found the value of the function at x1, which we are calling it fx1. And then we found the equation of a tangent line at this point, right? So let me make a tangent line which is kind of like this. And this tangent line gives us the second point, x2. Correct? So this was the process which we discussed just now. Now let's find a formula to get the value of the second point, right? Now, what we know here is that we have a point and we have a point, let's call this point as P. So point P is given to us as x1 and the value of the function at x1, clear? Now slope at P can be given to us by the derivative at x1. So that gives us the slope, correct? Using slope and a point, we can actually find the equation of tangent line. So y minus y1 equals to slope m times x minus x1, right? So we're trying to find equation of tangent line. In our case, it is y minus y1, which is the value of the function at x1. Slope is the derivative at x1. X minus x1 is the first point which we have started with. Now, the idea is to find the x2. Now, what is x2? x2 is the x-intercept, right, of the tangent. That means at this point y should be equal to 0, correct? Substituting y equals to 0 here, we get 0 minus f of x1 equals to derivative of the function at x1 times x minus x1. Perfect. Now this point gives us x2, right? So the x-intercept is x2. So this value of x, which we can isolate, will be x2. So okay, so we can divide by the derivative. So we get negative f of x1 divided by the derivative at x1, and that is equals to x minus x1. So we can isolate x from here. So we get x equals to, taking x1 to the left side, x1 minus f of x1 divided by the derivative at x1. Correct? And this is the next point. So this is the next point. Correct? So from here, x2 is this point, right? So from here, we can actually get a general formula. We can repeat this process. So the general formula is that the next point, xn plus 1, is the nth point minus the derivative minus the ratio of the value of the function divided by its derivative at xn. Clear? So this is the formula which we'll be utilizing to find the next values of x2's, and you'll find that if this process is repeated, x2 approaches, in this case, the root. Do you see that part? Correct. So that is the formula which we are going to utilize. So I hope the derivation is straightforward, simple to understand. Now let us see how to utilize this information in finding roots of equations which have values which are not integer values. Perfect. And this is a very efficient method which is normally used in most of the calculators and computers to compute solutions for equations. So let's take a few questions based on what we have just learned. So here is the first question for you. It's a multiple choice question. You can pause the video, answer the question, and then look into my solution. Suppose the line y equals to 4x minus 5 is tangent to the curve y equals to f of x when x equals to 2. If Newton's method is used to locate a root of the function of the equation f of x equals to 0, find the next approximation, right? 4 choices are given to you. Now, how are you going to solve it? When we say find the next approximation, that means we can directly apply the formula. So the next approximation is at, we say x2 is the x-intercept of the tangent, correct? Clear? Now since we are given equations y equals to 4x minus 5, for y equals to 0, let's find the x-intercept. We get 0 equals to 4x minus 5, or 5 equals to 4x, or 5 over 4 is equal to x. So option D is the right option. Is that clear to you, right? So let's recall, understand this process, right? So the idea was that if you start from one point, and then take a tangent line, the next point is the x-intercept of that tangent line. And this question is basically based on that concept. Is that clear to you, right? So let's take another question. The question now is, for each initial approximation, determine graphically what happens if Newton's method is used for the function whose graph is shown below. So for each initial approximation, let's say you start with A, will you get the result? How fast will you get the result? This is what you need to discuss. If you start B, will you get the result? That is the question which is to be answered. You can always pause this video and then answer your question, right? Now let's see what happens when we start at A. So if we start, that means we're taking x1 as equal to A, for example. In that case, what happens? So if I have A, then the tangent line will have x-intercept somewhere there. Now from here, I can get the second value, and next tangent will be giving me somewhere there, and then we will have a horizontal tangent as it seems to be an asymptote, right? So in this particular side, we may not get a solution. Correct? So we do perform iterative process, but we do not get solution. Perfect? Now what happens when you are at B? So if you start at B, in that case, your tangent is horizontal, right? So we have a horizontal tangent. Correct? So the method cannot be used. since we do not have x-intercept for this, correct? Right? Even otherwise, let's remember the formula. So xn plus 1 is basically xn minus f of x over the derivative of this function, correct? So if the derivative is 0, then you have no solution. So remember, we have a restriction here, right? We have a restriction. Restriction is that the derivative is not equal to 0. So if you get that, you cannot actually use this particular method. Clear? Now let's take point C. Now if I use point C, then a tangent here, for example, will have an x-intercept somewhere here. So if I use this point, right, in that case, I could be in a position to get away from the solution, right? So, or, now this is kind of critical point, right? So here, I may get a situation where the tangent is kind of like this, well, kind of landing on the other side and no solution, correct? So again at C, not a good point to select. As the iterative process will not converge to the solution. Right? Now, this C could be also such that you may land up here, right? And then you have a horizontal tangent. You see that part, right? So somewhere on this line, you may land up into a point. Tangent will have x-intercept whose value will be resulting into horizontal tangent. So again, no solution, correct? So that is another way you could see that Newton's method should be applied very judiciously. So what you see from here is idea of graph is important, right? So if I now use D as my point, in that case, I do get a value which gives me the result very fast and I get one of the solutions. Is that clear to you, right? So D, it is a good point. And get accurate value in few iterations. Now, whenever we say accurate values, we may say, let's say 4 decimal point. Is it okay? Something like this, correct? Fairly enough, right? 4, 8, whatever. So you can get a very good accurate value, not exact, approximate, in few iterations, correct? So what we note from here is that rough idea of graph is essential, right? So rough sketch helps to identify starting value or initial value. Is that clear to you, right? So this is a very important conclusion about using Newton's Raphson method. Perfect. So I hope this concept is well taken. Now, let's take an example to really calculate a value. Now, let's take another example to end our video. Find the fifth root of 2 correct to 4 decimal places, right? So that is to say we have to find fifth root of 2, correct? I'd like you to pause the video, answer this question, and then look into my suggestions. So let x be equal to the fifth root of 2. Correct? So that means we could say x to the power of 5 is equal to 2, right? So taking power of 5 on each side. So that gives you the function, which is x to the power of 5 minus 2 equals to 0. So we are actually looking for solution of f of x equals to x to the power of 5 minus 2. Is that clear, right? Okay. So we'll use Newton's Raphson method to find the solution. So we also need the derivative of this function, correct? So derivative of this function is 5x to the power of 4. And we know the formula is the iterative process where we get the next expected approximate root as previous minus value of the function at n divided by the derivative of the function at n, right? So that's the formula which we need to use. With this information, I think you can always pause the video and answer. Well, and the critical point is, what could be the starting point? So let's take x1 as equal to 1, correct? We're expecting this to be more than 1, correct? Okay, so let's now begin. So we are saying that x1 is equal to 1. Now we need to find what x2 is. Clearly, x2 using this formula is 1 minus value of the function at 1, right? So the value of the function at 1 over derivative of the function at 1, correct? So it is 1 minus value of the function at 1 is 1 minus 2 divided by derivative of the function at 1 is 5, correct? That's what it is, which is 1 plus minus 1 becomes plus 1 over 5, or you could write this as 5 plus 1, 6 over 5, correct? So that is how you get the second point using the formula. Is that clear? Now let's find the third point. So the third point, x3, is going to be, we have to start with 6 by 5 minus value of the function at 6 by 5 over the derivative at 6 by 5, correct? So let's use calculator now and find the solution, correct? So we are beginning with 6 divided by 5. So the idea here is you can place this value in the answer, right? So this is your answer. So if you start with answer, let's say equal to what? 6 by 5, correct? So that helps. So learn the way you can use your calculator faster. So we have 6 by 5. So we are putting here answer, and then we have minus, and we have to put this value. So let me put two brackets, one for the value of the function, x to the power of 5. That means answer to the power of 5 minus 2. Minus 2, bracket close, divided by, we need to divide by the derivative at 6 by 5, which is our answer, 5 times. So we can write this here, 5 times answer to the power of 4. Is that clear, right? Brackets close and equal to. So we get our value, which is 1.152901, something like this, right? Now, sometimes in the question it is specified, write this to 4 decimal places or whatever, correct? Now, since we want answer to 4 decimal places, it's a good idea to use at least 6, right? So 1, 2, 3, 4, 5, 6 we are using, right? Okay, let's take one more, 7, 8. Let's go with all the values given on the calculator. Fine, no problems. Next value 4 will be what? Let's calculate directly. So we have the answer, so we just put that answer here, minus brackets, value the function, which this is the formula, right? So answer to the power of 5 minus 2, bracket close, divided by derivative 5 times, let's close the bracket, open the bracket, 5 times answer to the power of 4, correct? Answer to the power of 4, bracket close, 2 brackets, equals to, so we get a value here which is 1.1487288, there are 387, correct? Now let's find x5. So I hope the process is clear to you. So you can always do this. So answer minus these 2 brackets, value of the function, which is answer to the power of 5 minus 2 divided by the derivative of the function, which is 5 times answer to the power of 4, right? So bracket close, 2 brackets, we get the value as 1.148698357. Let's find the next value. Now you see 148 is matching, right? Let's continue this process. So it's an iterative process. Answer minus the value of the function, which is answer to the power of 5 minus 2, bracket close, divided by, within brackets, 5 times answer to the power of 4, brackets closed. So that gives you 1.148698355. Now, we want up to 4 decimal places, and we see this is, we got answer almost up to 7 decimal places. Correct? You can actually continue this process and get to 8 decimal places also. Perfect. So that is how you could do. So we got this value. So our answer here is, the answer which we have got is 1.1486, right? Since we wanted 4 decimal places, we have this answer. And if the question was up to 6, we could have given answer as 1.148698, right? So that becomes up to 1, 2, 3, 4, 5, 6 decimal places. So that is how you see how easy it is to calculate the answer using Newton's method. And kind of it's important to select the right point also so that it converges faster to the value. Now this is extremely important method to find approximate solutions to equations. I hope it is completely understood. Feel free to write your comments, share your views, and if you like and subscribe to my videos, that'll be great. In this playlist, I will also share with you some questions which have been seen in international test papers. That will help you to understand the topic better. Thanks for your time and all the best.